Thank you, everyone. Thank you, Christina, for introducing me. My name is Jared Smith. Our paper is Routing Around Congestion, and it's about routing around DDoS and other new forms of DDoS in ways that don't require cooperation. This paper was co-authored with my advisor, Dr. Max Schuchard, and we're from the University of Tennessee. So I want to begin by asking, do we still care about DDoS? These things, this has been a threat for a long time, and people continue to push it under the rug, but it keeps popping up. In 2017, there was a particular statistic by Kaspersky directed by their AV engines and other network infrastructure that on one single day there was 994 attacks all across the network stack. Beyond that, there's a new form of DDoS called TransLink DDoS, which was presented in literature in 2013 at S&P and 2009 at Historics, which targets links outside the control of the victim, thus totally defeating any sort of normal mitigation mechanism. So it's taken entire countries offline, like Liberia. That's what was responsible for the Dyn attack. And Oracle and Dyn are some of the largest companies out there and could do nothing against this because of, if it's outside your infrastructure, there's nothing you can do. So we built a system called Nix, which we believe is the first system to actually mitigate TransLink DDoS, this new form of DDoS, without cooperation, without requiring CDNs, without filtering, and I'll talk all about that, and without relying on more new protocols, new deployments of things that you can't do right now and would require waiting time for people to push stuff out. To do that, we treat DDoS as a routing problem and not a filtering problem. We don't throw more infrastructure at it. What we do instead is we completely route around the congestion, building on techniques prior and adding our own to do that. And then we can isolate the victim traffic from the attack link, and I'll talk about that in a bit, the advantages it gives us. But the cool things is we don't need a filter, which is how 90% of the things out there say you want to do it. We don't need to classify traffic at all in this case either. We don't need help. We don't want to drag more traffic along, and I'll show we don't do that. And again, we don't have to we don't require deploying new protocols or waiting on things to go out there. So first, I'm going to talk a bit about internet routing. So we like to think of the internet as this large cloud that sits out there and we talk between two places. But it turns out really what it is a bunch of these things called ASes, or autonomous systems. And these are large businesses, large single entities that have a lot of networks within them. And the de facto routing protocol between these is called Border Gateway Protocol, or BGP. The latest version, version 4, was updated in the mid-2000s, but it's been around since the dawn of time. And like a lot of other network protocols out there, they didn't really design security into it from the beginning, so things have been strapped on top of it, like BGPsec, similar to things like SSL and DNSSEC, that are out there but not really going to stop anything like DDoS. So with BGP, a lot of ASs out there, they will push their paths forward. So they say, hey, the path to me, my prefix is through me. And it keeps propagating throughout the internet, eventually reaching and converging throughout the topology. And the thing here to keep in mind is that the forwarding AS, the AS which is receiving paths and getting advertisements, chooses which path to forward, and on top of that, from the data plane, there is always one best path to a given prefix, even though, as we'll talk about, there are other paths that exist, and that's where our contribution comes in. Okay, so that's BGP. You can read more about it, talk to me after, refer to the paper, ask a question, but this talk is more along the lines of building on top of that. So let's kind of re-go over DDoS, just to give us a good perspective. We all think of traditional DDoS as this thing where there's some botnet out there, ignore the distribution here, let's just say it's downstream, and it comes and attacks your AS directly. And so what's going to happen is the traffic is dropped all along the way. And on top of this, it's really hard to filter flows that are of massive sizes like we're seeing now. A lot of times people have to deploy lots of infrastructure, and a lot of times people will even go forward and use a CDN like Akamai or Cloudflare. But the problem with these CDNs is not only does it often cost a lot of money, and I know there's some free services out there for it as well, but these things make it a war of bandwidth. And it's just who throws more bandwidth at the problem. And I don't know about you, but I don't really like wars that just require more money to win. On top of this new form of DDoS, TransLink DDoS, totally changes the game and how this whole game is played. So instead of attacking the victim directly, the traffic hits links upstream and focuses its traffic by controlling the botnet in a certain way, and then directs it to wanted locations. This way, the victim never sees the traffic, even though it's dropped upstream and out of their control. You can't use a CDN here. You're not going to be able to even see your traffic in the first place. You can't filter it. And I didn't mention this before, but filtering requires you to classify benign versus malicious traffic. And if any of you have seen some of these machine learning talks, adversarial machine learning is a thing, and it's getting a lot harder. On top of this, these transit ASes make money by transiting the traffic. So they might not even be incentivized to drop it upstream. So that's where we come in. We built a system called NICS that routes around congestion by recognizing one very important thing. The alternate paths on the internet exist even though there's one best path. So we build on some existing primitives out there to control these paths and route around attack links. By doing this, we isolate the victim traffic. We mitigate traditional DDoS as well in cases where even if you're attacked directly, we can route you onto other links that you can use. And finally, we make the attacker bandwidth irrelevant. So even if you have a massive botnet like Mirai totally hitting you, as long as you have other links upstream, which the internet's path diversity is very large, then we can route you onto new paths until we find one that has enough capacity to handle it. So in practice, let's take a look at this and see what it looks like. We're going to look at TransLink DDoS here, where you have a victim AS downstream. This is also a deployer in the paper. They're deploying NICS. And there's some upstream critical AS. When you see this here, there's one critical AS. We've started work on doing this for multiple too. But for the purposes of this talk, we are protecting a single very important person or picking one or the other at given times to always protect their traffic from these attacks. So there could be some normal path here. And there's a botnet up here that wants to target and send the traffic upstream of this link. And so what happens is now that link is impacted, and you're going to start dropping traffic there. On top of this, the victim, in this case, can see that, hey, for this critical AS, I do not see the traffic from them. It's being dropped. And on top of that, I don't directly observe an attack on my AS. And there is some prior work just in the last few years about locating transit links that are targeted as well, so you can leverage that to figure this out. So what we do is we shift onto the alternate path, knowing they exist by examining the topology, which you can do with open data. And when we shift on that alternate path, that link upstream is still impacted, but now we're leveraging an alternate path and making that attack traffic totally irrelevant. So in this way, we can control the reverse path back to you. OK, this brings up a good point. How do we use alternate routes? Well, BGP lets us adjust outbound traffic by choosing a preference of who we send our traffic to, but it does not let us control the path inbound traffic takes to us. As I mentioned earlier, every AS decides which path they want to forward, and every AS has a best path to a certain prefix on the internet among all of them. But there's no way for you downstream or upstream, wherever you are of that AS, to say, hey, I really wish you would send it over to this link or this link. Well, we could talk to them. We could say, hey, AT&T, L3, whoever, other university, please use this. But legal teams are not the best to work with. We have to use contracts to do this. We have to buy services, and that makes it really hard. So what we do is we take away the upstream AS's path to the deployer. And by doing this, we use a technique called BGP poisoning, or in our paper, fraudulent route reverse poisoning, to take away that choice and force them to use a path that they wouldn't have otherwise used that goes around the around the attack link. OK, so in detail, this is a bit what FERP looks like. So we have some victim AS, that, which is 1 in this case, and some critical AS, which is 3. And the normal path is over 2. And in this case, the critical AS prefers going over 2 than 4, and the victim can do nothing about it normally with BGP. But it turns out there's some kind of attack there that we want to avoid. So what we want to do is we want to leverage a property of BGP called loop detection, which says that when you receive a path to a prefix that already has you in it, you will drop that path, or at least you should if you agree with the protocol. So when this happens, 4 will get that path and tell 3, hey, you can still reach 1 over me. But 2 will take it and say, hey, I'm already on the path, so I'm dropping this. And now what happens is 3 no longer even sees the path over 2, and they will take the path over 4. Now you may be thinking, does this affect other people other than me? Am I poisoning others? Well, no, I'm only poisoning myself. And in fact, this kind of technique happens a lot on the internet now, but for other purposes, for aggregating prefixes and getting traffic around you locally, not so much for routing around major upstream events. The nice thing about this is that we can do this with normal BGP with configs applied to your router. And in fact, it's not really a config. It's literally just advertising paths. And this whole paper in general was done in simulation with real, very realistic data from the actual internet. But does it actually work on the real internet? Well, that's a paper we have coming out. And in fact, this actually does work and is running out of 12 different routers across the world. But for our purposes, I'm going to show you what this will look like with huge adversaries coming at us. So this brings up a good point. If we can route onto alternate paths, do those other paths that we are propagating, does that in fact get to other people and then be like, hey, I lost a path through here, but I see this new one that opened up? We call this disturbance, and we have to actually deal with this because what can happen is we can drag along attack traffic onto these links. And to do this, we use a technique called pathlining, which prevents the spread of these paths throughout the internet except to the people we care about. And on top of that, we use FERP kind of on itself to do both of these things. I apologize for my speaking. I need water, so I do not have a lisp, I promise. So with disturbance, this is basically how it works. There's a normal best path, which is going here, but there might be an attack there. And what we want to do is we want to send out FERP down that path. And what could happen here is, just like I showed you before, the path is going to start spreading and spreading and spreading in a way that we could disturb potentially thousands of other ASes. And now, this is really bad because, first of all, you only want that critical AS to move on to a new path. But what's going to happen is we're going to drag everybody else out there, regardless of a website, onto a new path, thus making us even more congested than prior. So we use a technique called pathlining. Thank you. Appreciate it. OK, that's much better. I can actually speak now. So again, like I said, we use FERP. We shoot it out to the internet. And now what we do is we append the bordering ASs onto these paths. And when they get it, the same property comes in. They start dropping that path. And now there are no new paths to us except for the people we actually care about. Now, this brings up another point. Well, not only do we need to route onto an alternate path, but we need to route onto paths that have capacity to hold us. So we use something called searching, which it sounds like just what it is. We find paths with sufficient capacity. We can also make sure you don't search beyond what you really need to, optimizing for certain performance metrics. OK, so what does this actually look like? So in simulation, we use an event-driven simulator that models topology and the traffic in the internet. 60,000 ASs roughly at the time, and we pull AS relationships from actual BGP collectors. We leverage modern botnet models like Mirai and Configure and others, and bandwidth models. We simulate TransLink and traditional DDoS. Refer to the paper for more of the details, but the big thing I want to talk about is bandwidth. Because bandwidth on the internet is something that's really hard to model, and there's no ground truth for it. In the prior work, those prior attacks in most systems assume a uniform bandwidth. And the reason there's no actual bandwidth model out there that says between every AS there's this much capacity is because just think about it. If someone like AT&T said, hey, I can handle 10 gigabits per second, Verizon's going to come along and increase themselves to 12 and market that and say, you should use me instead. So even though this is the case, we still need to model the capacity of each link because we need to know if we can shift people onto links with enough capacity, and two, if those links have enough capacity plus their additional normal traffic to handle our new load. So we model the bandwidth with 3 different models to show that regardless of the model used, with more complex ones that are based on using a ground truth data set of some small reportings of ASs that say, I have this much transit traffic, and then we basically add a bunch of other features like the AS size and other things to say, of the 10,000 ASs where we have some model of what they say they have, we're going to train a classifier and predict the other 50,000. And just to show this is independent of the complexity of the model, we do it with a degree. So the more connections you have, the more bandwidth. The more IPs, more prefixes, the more bandwidth. OK, so before we actually show this works, we need to route onto alternate paths. We need to not drag along non-critical traffic, which we don't care about, or attack traffic. Most importantly, we need to route onto alternate paths with less congestion or no congestion whatsoever. Because in this way, without relying on CDN, without relying on help, right now on the internet, we can stop these ridiculous forms of DDoS from happening and move you on the path with sufficient capacity. And lastly, just to show this actually works, trust it, you can believe it, we want to work independent of the botnet model or the bandwidth model. OK, so does it actually work? And this will be the most fun part. So feel free to clap if you want at every single graph. Just kidding. OK. So the premise of a lot of these graphs is that they are pretty boring in the sense that boring means they worked really well. But along the x-axis here, that is saying that is the number of hops out from the victim at which the attack is focused. The two colored lines show both TransLink and traditional. Even though the attack is focused upstream, the attack is still being directed to the victim in the case of traditional. And in the case of TransLink, it's directed to other bots. Talk to me after, look at the paper. There's a lot more graphs. There's a lot more explanation of that methodology. But what this says is that for the worst case, on average, 95% of the time, regardless of the attack, we can move tens of thousands of cases of ASes in the real topology onto a new path or onto multiple new paths. So that's our first primitive. First, we can route you into alternate paths. Next, can we actually not disturb people? Well, it turns out using pathlining, we only alter the best paths of about 10 other people. Without pathlining, it's about 6,000. So obviously, that's why we need that, because we're going to drag along that many people. And here's the kicker. The thing we really care about, what we're getting to care about, is can we move you onto paths that are less congested? So in the case of traditional DDoS, the x-axis here, again, is the distance the attack is focused out. You are being directly attacked here by a botnet that is congesting that link 5 times more than it can handle. That's why the CF, or congestion factor, is 5.0. 95% of the time, with traditional DDoS, we can route you onto paths that have capacity to give you some alleviation. 75% of the time, with this very hard form of DDoS, we can give you less congestion, or we can give you absolutely no congestion on those paths when we can route you into alternate ones. So this already says that with a traditional DDoS, something the size of Mirai with 2.8 million bots, we can hit you directly, and you can find a new path with the ability to handle it 75% of the time. The biggest and most fun thing is that TransLink DDoS is essentially solved if you deploy this right now. 99.9% of the time, TransLink DDoS, you don't filter, you can't have a CDN, none of that. We can get you a new path with less congestion. And with absolutely zero congestion, 95% of the time, these attacks are gone. Refer to the paper for more of the details on this. The TransLink and traditional are independent of the botnet models. And in terms of ongoing work, like I said, this actually works in simulation with real data. But we have a paper coming out of this working in practice. And we have a few steps forward in how we want to do this with multiple criticals, multiple deployers, multiple people do it at the same time, and moving target defense. My name's Jared Smith. Like I said, Nix is the first system to really truly mitigate TransLink DDoS without paying people, without requiring help, and on your network right now without bothering other people. Thank you so much. Yeah.
So I have a, I have a quick question. Can you tell us a little bit about how do you detect congestion?
Yeah. So naively, what you can do is, like I said before, if you are some downstream AS and it's TransLink, so it's upstream of you, you can say, okay, I normally have this much traffic from some supercomputer or some education network. Now I don't see it. Or 2, you can say, hey, my performance loss is suffering. But if you refer to the paper, there's a number of papers that were at NDSS and others that kind of show you, without getting help from others, just like we want to do, can we detect a link upstream that is impacted? Yes?
Ken Calvert, National Science Foundation. My question is similar. I guess I'm wondering, since there might be a large number of ASes downstream from a transit link that's several hops away, I'm wondering how this works when a number of ASes conclude that they're under attack because of this congested upstream link. And I'm wondering about stability of BGP is sort of notorious for taking a long time to converge. So,
yeah, so there's 2 parts there. One, if a bunch of people do this shifting at once, that is something we are looking at now. But second, with convergence, a lot of people like to think BGP and routing converges in 20 to 30, 40 minutes. Well, we are testing these updates in 2-minute intervals and finding tens of alternate paths in the actual internet with real traffic. So you can shoot an advertisement out, and within 2 minutes, you can start shifting that traffic away from the attack with thousands of cases of real ASes. So convergence is really no longer an issue, and that's really the fun part about this.
Hi.
Yes.
Robert Licho from MIT Lincoln Lab.
Okay.
Very interesting work. I have a couple of questions, kind of following up. How sensitive is Nix to attacks on BGP, and have you given a thought to that? And also, have you thought about the attacker potentially adapting to NICs switching routes and then attacking the paths that you switch to?
Yes, so towards the first question, as this is mostly for my PhD, that is something I've thought a lot about and will be doing. We consider threat models where the adversary is a large botnet. It's somebody that controls it. And in most of these DDoS attacks, it is not a routing-aware nation-state adversary. And if it is a nation-state, they're just buying a botnet and sending it. So it's a good point. Talk about that after. I know that's of importance to our country deploying this. Second question is, can you use this adversarially? Absolutely yes, and we're doing that right now. Look for that hopefully soon.
Thank you.
Yes, thank you.
WSV Weg, TU Delft. I was wondering if you could also implement your approach with BGP communities.
Yes, so we're actually working on this next paper, doing this in practice with one of our network operators. And he would know a lot more about that. Personally, I don't know too much about communities. But you can do this with normal AS path. Like I said, you have panned ASes you want to avoid to the end. And in practice, this kind of falls apart with certain cases. Large ASes, the people that have the most connections like to filter out other people that they don't think they're connected to. So there's ways to get around that, but communities might be an approach. We should talk after if you have a good idea. Thanks.
Hi, Jacob
Yes.
Czar, U.S. Department of Defense. So my question is, I was under the impression that most modern day DDoS attacks, the point of failure is actually in the last mile of the internet connection, because it's where all of the attacks converge. And in that case, whether it's the last mile or the actual server that fails, you can't really route around that. So feel free to correct me if I'm wrong. And if that is the case, I was wondering if you comment on maybe next steps to try and solve that problem.
So let me clarify really quick. Are you saying, well, first of all, let me answer. The TransLink DDoS that's more along what we're seeing now, and that is not, if you consider the last mile of the upstream link, then yes. But if you are the Department of Defense and you communicate with a base in Iraq, they will target the deep sea cables into the Atlantic, and there's nothing in the last mile you can do there. Second, from your other question was, does that answer that? I think those are kind of related.
Yeah, I guess I should do more research and I'll talk to you more.
Yeah, find the paper. Those two attacks are called Crossfire and Core Melt. I'd love to talk more. Please, come find me. Yes?
Sven Dietrich, City University of New York. So just a comment about what you call TransLink DDoS. It's been existing since the early 2000s, so it's not that novel. So if you look at the bots from the early 2000s, they already had the capability.
Yeah, I mean they do, but we still see it happening. So and there's
Right,
nothing stopping it.
It's not really what you call modern. It's been around for quite some time.
Yeah, I agree. I agree those kinds of things existed. On top of that, I've read some of those prior papers, and remember the internet was like 5,000 ASes. I mean, less than that. We're dealing with 60,000 and tens of billions of paths. So it has changed, but yeah, I agree.
Let's thank our speaker.
Thank you so much.